Hi, and welcome to another physics class. In today's lesson, we're going to talk about parallel circuits. I'm going to go ahead and explain the reasoning behind that negative L or the negative 1 in a few minutes. But the two diagrams that we see here depict the same thing. The diagram on the left is actually correct now, whereas the light bulbs are both lit the same way. That's because each one has the same exact power source coming to it. Each one has a wire directly from the power source, so they both get the same voltage. So the voltage drop for a parallel circuit would always be the same at every single resistor or every single branch. Now with parallel circuits, there's always more than one path, whereas with series, we only had one pathway. And devices can be operated independently, which means that if one bulb goes out, the other stay lit. Or if there's an opening in a switch, or if there's a switch that is open in the circuit, the rest of them can operate. And that purely depends on where that switch is. So there's two types of opens. There's an open in the main line, and there's an open in the branches. The diagram that we see here, they have A1, A5, and so on. That's actually for the currents, but we're going to pretend that we have switches at those places. So let's talk about if there was a switch at A1 or at A5. That would be considered on the main line. If you have a switch at either one of those positions, and if it's open at either one of those, then the whole circuit is down because there's no way for the power to go through. However, when it is open in the branches, let's say that at A2 or A3 or A4, then the rest of them would work. So let's look at this picture and imagine that there's the only switch that we have here is on A2. And if at A2 it is closed, everything is functioning. If A2 is open, then the second resistor with the 3 ohms and the third resistor with the 4 ohms are still operating. So it just purely depends on where the opening of the circuit is. Now, resistance in parallel. So this is why you see that weird negative L that I write there, and I want you guys to start writing it the same way. And it's because to calculate the total resistance in a parallel circuit, you always have to take the inverse. So as you see in equation number 39 in our formula sheet, it says that it's actually 1 over RT and not RT itself. So when you do these problems, and we'll do a separate one on the math portion of it, you're going to go 1 over each resistor plus 1 over the other resistor and so on, and you're going to get some decimal point answer. And you want to take the inverse of that. So you can either do 1 over the final answer, or you can just hit that same answer to the negative 1, to the power of negative 1. So there's the reasoning behind why I write parallel the way that I do. All right, so voltage in a parallel circuit. Voltage drop across each branch in a parallel is going to be the same. This is because all branches are connected to the same wire. So if we imagine that there's a 9-volt battery and we have 3 resistors in 3 different branches, each one of those is going to receive 9 volts because they're able to draw the full 9 volts from the battery at the same time simultaneously without experiencing a drop in terms of lowering as we did with series. So the difference here is in the series circuit, voltage drop, it would reduce, and the bulbs would get dimmer and dimmer. Within a parallel circuit, the voltage drop is the same amount as the battery at all times. So each branch and each resistor is able to get the full amount of the voltage from the battery or the power supply. When it comes to parallel circuits, the current splits as it goes through the branches. So the sum of the current in the branches will equal the current in the main line. And the current in the main line is also going to be referred to as the total current. So as we look at this diagram, the total current is the ones with the 3 amps with the 2 big blue arrows that we see at the beginning, one at the top and one at the bottom as it's returning to the battery. And that total current, as you can see in each branch, is getting reduced, and there's another amount of current going away to each branch. One easy way to think about this is to think about it as each branch being a different lane in a tollway. And each one of those light bulbs represents a toll tag. The more lanes that you have, the more cars are able to go through, and you're going to have a greater total current overall. Now, the amount of current that goes through each branch is going to be inversely proportional to the resistance in that branch. So when we're talking about branches, the more resistance you have, the less current you have in that branch. To calculate the current in each branch, we're going to apply Ohm's law, and that's simply I is equal to V divided by R, and the subscripts depends on which branch you're looking at. In this case, we're looking at branch number 1, so it's I1 divided by is equal to V divided by R1. And if you're thinking about why there is no V1, well, that's because in a parallel circuit, remember that each branch, the voltage drop is always going to be equal to the same amount as what it was originally from the power source. In order to calculate the total current in a circuit, you apply Ohm's law to the entire circuit. Sometimes you see them as R total or R equivalent, and they mean the same thing. It just means total resistance in this case. All right, so there's some advantages to parallel circuits. For example, we have a picture here, and it's a simple picture depicting a car. And in a car, you've got one battery, but you've got a bunch of different wires to it. And you can have lights, you can have horns, radios, and they're all going to be in parallel circuits so that when you turn on your lights, the horn and the radio don't go off. And likewise, if you use your horn, you don't want everything else to go on. So there's advantages like that. And then every outlet obviously gets the same amount of voltage. So we talked about this when it was light bulbs. Every light bulb is able to have the same exact output of brightness, whereas in a series, it kept getting dimmer and dimmer the further down it was in the line. There's, however, some disadvantage to a parallel circuit. The more current that you have going through means that it could overheat and eventually cause electrical fires. And electricity in your home, they're going to be wired in parallel circuits, and the appliances are all running at once, so the total resistance drops, and you have more current going through the wires. And as the extra current goes through all these wires, you're going to have added thermal energy, which is basically heat that could possibly melt the insulation of the wires, and it could cause short circuits or fires. So in order to prevent that, we have ways to protect against it, and you've got fuses and circuit breakers. So if you ever notice that, a section of your household goes down and you have to go and apply the circuit breaker and put it back on, the reason for that was a safety feature. So, it's essentially to open stop all currents if the current is considered to be too large. And you've also got ground fault interrupters in order to prevent dangerous shocks. Okay, so that's it for the concepts. Tune back in for the math portion, and that will be a super easy one once you get the hang of it. Hope that this video has been helpful. Thank you and have a great day.